the scalar top search.
Thank you. And good afternoon, everybody. So today my topic is scalar top Quark search. I will answer those questions. So first, what's the scalar top Quark and why we are interested in, and then where to find it. So here's the outline. So first, I will introduce the standard model to you. And the standard model is a very beautiful, complete model. And in the standard model, I will talk about all the particles in this model and the Higgs mechanism and the lattice problem in this model. And then we move on to the supersymmetry. So the first question is, now the standard model is very complete, why we still need supersymmetry? So I will answer this question and then introduce some particles in this model. And I will emphasize this particle, the scalar top quark, and how it decay, and what's the current experiment constraints. Then I present one of my analysis and results. Finally, go to the summary. So in our freshman physics, we already learned there are 4 fundamental interactions. So the gravity, the electromagnetism, the weak, and the strong interactions. So for the gravity, Newton found the gravitational law by the falling of the apple. But it seems nowadays many people use apple to play Angry Birds. And for the electromagnetism, so any interactions involving photons is the electromagnetic interaction. So it happens in our everyday life. And for the weak interaction, this is the energy source of the star burning. So, and also for the strong interaction, it happens between the quarks and the gluons. So we know there are 4 interactions. So we need a theory to describe those interactions, right? So the standard model is the theory to describe 3 of them, not all of them. The electromagnetic, the weak, and the strong interactions. And in this model, those are the elementary particles. So those 3 columns are the fermions with spin 1/2, and which contain the quarks and the leptons. And also there are 3 generations. I mean the difference between each generation, just the mass. So the mass will be higher and higher from the generation. And then those are the gauge bosons with spin 1, and those are the force carriers for the 3 interactions. So this is the photon, and which is the force carrier for the electromagnetic interaction, and it's massless. And this one is the gluon for the strong interaction, also massless. And those 2 or 3 are the Z and W bosons for the weak interaction. However, those 3 are massive. So if you learn some quantum field theory, you know we cannot write any arbitrary mass term in the Lagrangian because it will violate some symmetry. So the question is how those particles gain the mass. So it means this is not complete. We still miss something, right? So one very simple solution is we introduce some scalar field, so which is the Higgs field. So after spontaneous symmetry breaking, the 3 degrees of freedom of the Higgs field will be eaten by the W and Z boson. So then those 3 particles gain the mass. And the left degree of freedom is this one, is the Higgs boson. And this theory was built about 52 years ago maybe. And then the LHC spent decades to find the Higgs boson. And finally, in 2012, they found it. So this one is just a picture to show the signal from LHC. And this plot shows the signal has a bump over the backgrounds in the mass around 126 GeV using the data between 2011 and 2012. So you can see here we found something. and they just confirm this is the new particle similar to the standard model Higgs boson. So now we find the Higgs boson. It seems the standard model is quite complete now. So we have the quarks, the force carriers, and we have the Higgs boson to give mass to those particles. So now it seems it's quite complete. And this situation is very similar to the situation about 100 years ago. So do you still remember a lot of Kelvin said there are two little clouds in the sky of physics? So now we already find the Higgs. It seems there's no cloud at all. So how do you think about it? Okay, so you do physics, you may know physics is not kind. So as one of my physics 181 students said, the physics hurt me very much. So here the same. The Higgs boson mass is hurt by the quantum fluctuation. So here I show here is the quantum corrections to the Higgs mass. So the Higgs propagator and top quark to the corrections. So the physical Higgs mass you can see from here is will be the bare mass plus the corrections. And unfortunately, this correction is quadratic divergent. So if we take a cutoff, the cutoff is very, very large, it's around the Planck scale. So you can see this term is huge. And from an experiment just 2 years ago, we know the Higgs mass is around 100 GeV. So it means we need this very large term to cancel out the corrections. So which makes those two unnatural, right? So how do we solve it? I mean, one very simple solution is we fine-tune this one to cancel out this. But you should fine-tune it very carefully. You can see this is huge, this is very small. So you should fine-tune it like this. You should be careful. And this is one solution, fine-tune the parameter. But it seems you need to be very careful. And also physics not easy, so maybe not easy to do it. So another way is we can introduce symmetry, right? So this one we already see the Higgs propagator with the top in a loop to the quantum fluctuation. So if we assume for each fermion we have a bosonic partner, which also will introduce the correction through Higgs. And this one we also have the corrections. And you can see those two corrections exactly the same with opposite sign. So you can see those two can be cancelled out very nicely. So this symmetry will recover the light Higgs mass because the corrections already cancelled out. So this symmetry relating the fermion with the boson, we call it supersymmetry. So becomes the supersymmetry. So that's the reason why we introduced the supersymmetry to recover the light Higgs mass. So as I say, the supersymmetry is the symmetry relating the fermions and the bosons. So it means for the fermions in the standard model, so those particles, the fermions in the standard model, there are bosonic partners in the SUSY model, right? So those are the scalars, the bosons. And for the bosons in the standard model, so those 5, there will be the fermionic partners. So those are the fermions. And I should mention, the supersymmetry is not exactly symmetry, it must be broken. So, do you know why? No? Okay, so as I said, the supersymmetry, just the symmetry relating those two different particles, the fermions and bosons, right? So it means the other property should be exactly the same. So if the supersymmetry is an exact symmetry, so it means if this is not broken, it's an exact symmetry. So the mass between those particles with those particles will be exactly the same, okay? But in fact, we already found all the standard model particles. We already found all of them. However, we did not find any signal from the supersymmetry. So it means the mass of those two should not be exactly the same, right? So the mass for supersymmetry must be much, much higher than the mass of the standard model. So that's the reason why the standard model is not an exact symmetry. It must be broken. Okay? So supersymmetry must be broken. And also, you can see from here, there are many particles. So which particle we are very interested in? This is not very, important question, right? So as we say, the top quark and the scalar top quark plays very important role in the light Higgs mass. So we will be very interested in this particle because it's very important to recover the light Higgs mass. So you can see from here, you probably see this a few slides before. So if in the framework of supersymmetry, we have the corrections to the Higgs mass. So from the corrections, you already see the quadratic divergence already be cancelled out. So no quadratic divergence in this expression. And also we know the Higgs mass from experiment is around 126 GeV. So this is very strong in action. The stop mass should be around the TeV scale. Okay, so the TeV scale is about the search range for the current LHC. And also from here you can see it's very heavy. The stop is very heavy, so it cannot be stable. So it must decay. Okay, so the question is how the stop will decay. So for the current experiment search, we just assume the stop has two decay channels, either 100% decay to this channel or either 100% decay to those channel. Okay, so those are experiment search. So this plot shows the current experiment constraints on the stop mass. So for this channel T, the stop directly decay to B charginal. So this one, you roughly can see the mass around 600 GeV is being excluded. And for this channel, the stop mass up to about 700 GeV excluded. But they do some assumption, so those are 100% decay. But in the model, the stop decay actually depends various parameters. So for example, in this scenario, so the stop will not 100% decay to either this one or this one, right? So we have new channels opens up. So I have the plot to show the branch fractions of those decay channels. So from here we can see this channel is highly suppressed. The branch fraction is about a few percent. So it means the current experimental search limit will be much weakened. And then we have those two dominant decay channels, the charginal and this neutrino. Okay, so then we will use those two channels as our new strategy to find the stop. Okay, so in the LHC we have a proton-proton collide, boom, to produce the stop pair, and one stop decay to the B charginal, the other one decay to top. We call this the second neutrino. And those two are very heavy and also not stable. So those two will further decay to the stable supersymmetric particle and also the standard model particle. And those, I should mention this particle. This particle is the lightest supersymmetric particle. And this very stable and weak interacting with matter. So this is very good dark matter candidate. Okay? So for those final states, I look for one W decay leptonically and the other W from top decay hadronically. And also the Higgs will decay to BB. So you can see the final state contains 4 B quarks. So we have B quarks, and 1 B quark from top. So 4 B jets, 2 light flavor jets from W decay, and 1 exactly lepton, and a large missed energy. This missed energy will from this one, the neutrino, or from those are the missed energy, because this particle is weakly interacting with matter, so it will leave any signal in the detector. So this will be in the form of missed energy. Okay, so for this final state, we have the backgrounds. Those are the standard model backgrounds. You can see we have the TD bar, TDBB, TDZ, TDW, TDH. So you can see those are the corresponding cross sections. So you can see the TD bar, the cross section is way larger than the signal. Those are the signal. Okay, so it means we need use some strong cuts to cut down the TD bar, because the cross section is much larger than the signal. And also for the TDBB, those two will be the 2 dominant backgrounds. So I use 1 cut is the missed energy. So because in the standard model, the missed energy just from neutrino, and in the signal, in the SUSY, the missed energy will either from the neutrino or from the RSP. So for the signal, the distribution will be way wider for the backgrounds, right? So the backgrounds missed energy largely from neutrino, and the signal it came from both. So we have this distribution. So the cut, we will cut from about 100 GeV until to 200 GeV to select the best cuts. And another cut, we will look the transverse mass. So also the for the backgrounds, all the missed energy from the W decay. So when you reconstruct the transverse mass, you will have a peak around the W mass about 80 GeV. But for the signal, we have no such pattern. So you can see for a signal, it's wide, the range is much wider than the backgrounds. So we also have a cut around 100 GeV. So when we apply some cuts to enhance our signal and in the meantime to suppress the backgrounds, we have the results. So from these results, it presents from, I say this is RSP mass. This is the stop mass we are interested in. So from this plotting, the 5 sigma is the discovery reach. So you can see from here, in this plane, if the RSP mass is 0, so this one is 0, so the stop mass around here, 740 GeV, can be discovered in a 14 TeV RSC with luminosity 300 femtobar inverse. Okay, and the biggest reach can be around here 900 for the RSP mass of about 200 GeV. Or if we cannot find it, so we can set the exclusion limit. So the 95 exclusion limit will be about here 850 GeV for mass this RSP, or it can up to about 1100. Okay, and also we have, this is the stop, and also for the Spartan we have very similar final states. So we also do Spartan. So the limits for the Spartan is also very similar to the stop. So those two will have, the Spartan stop will have almost the same final states. So we will combine the results. So we have the combined results. So if we have the 14 TeV 300 femtobar, we can reach the stop mass above this. So let's see about 5 years later. Okay, so those are my main results. So summary, so as we say, the current research will focus on those two channels, assuming 100% decay, but we know that for different parameter spaces, there are different decay channels, so which can be utilized to search the stop, and we can reach this region. Thank you.
Could you explain more clearly what exact Chi1 and Chi2 is?
Oh, the Chi1 is the lightest supersymmetric particle. The Chi2 is the second lightest supersymmetric particle. So the mass will be a little bit higher than the Chi1. So the Chi1, Chi2 is from...
Could you go back to the slides where you show the supersymmetric particles?
This one?
Even before the particles, standard model particles, the little balls, yes.
Okay.
and then you can tell them what is Chi1 and Chi2.
Okay, so the Chi1, Chi2. Okay, so in the standard model, we have the Z boson, W boson. So in the supersymmetric model, we have the okay, so
Zeno, we know.
But if you learn the quantum field theory, so those actually are not the basic, the fundamental field. So the fundamental field will be the Bino, we know. So the Bino, we know will interact with the Higgs Zeno. So in the SUSY, we have two Higgs doublets. So actually, if you write down the gauge eigenstate, so you will have Bino. This is so the Bino, we know. Those two is so the combination of Bino will to form the Zeno and W. I don't know how to call it W. And you, as I said, you have two Higgs, right? So it means we have two Higgs Zeno. So for those eigenstate, so if you write down the mass matrix, then you diagonalize the mass matrix. So the lightest one we call it Chi1, 0. The second lightest one we call it Chi2, 0, etc.
What, for your Chi2s, to calculate those branching ratios, you must have assumed Chi1 and Chi2 being like, what did you assume? Chi1 mostly or?
No, actually we said, I mean the Chi1 mostly will, the mass will be mostly from the Bino.
So mostly Bino.
Yeah.
Okay.
And the Chi2 will mostly Vino. Okay. So we said the mass difference is 150 GeV. So to see the branch fraction.
There are also the other case where the Chi2 could be the Higgs Zenos.
Yeah, exactly.
But for the particular product he showed is for the Bino and Wino.
Yes. Okay. We will consider more and more cases.
I know that there are other naturalness problems in other areas of physics. Are they all formulated in a similar way, or are they?
Oh, you mean the Higgs problem? If it's related to Higgs, yes. But if related to other, maybe I'm not so familiar with.
For your result plots, the vertical is cross-section times branching ratio? Presumably?
Oh, you mean this one?
Your vertical axis there?
This one?
Yeah.
Oh, actually it's the significance. Yeah, we do not do so fancy systematic analysis.
Okay, just...
That's just the S over square root.
Okay.
Yeah.
Okay, just trying to understand what all of them are.
Are there any more, I guess, prominent channels that you can see that much missing energy?
Yeah. We will see different channels. For example, we have Z in the final state, so Z can decay to lepton. And you talked to me this morning. He said he's now doing the Z tagging using the leptons. So yeah. So we have Z. We can use the Z2 as one of our analysis.
I don't know if you've looked yet, but what's your requirement on the lepton PT here?
Oh, the laptop PT, we just require 25 GB.
Okay.
20 or 25, I forgot.
So triggers are going to become an issue.
Yeah, just the kind of beta trigger level.
Just because the trigger level is now going up.
Okay. Okay.
That's why I was asking.
All right, well, if there are no more questions, let's thank Juan again. And there are evaluation forms for this talk, so